Okay, hello everyone. Yeah, welcome back to school. And apparently, we all survived the earthquake. And for those of you who are from Hualien, I wish you and your family all the best. Yeah. Yeah, if you have any difficulty, let me know. But otherwise, may I remind you that next week is going to be our first midterm. Okay, next week at this time, Wednesday, will be our first midterm, and the first midterm will cover from the beginning of the semester to the last lecture. Okay, not including this lecture. Okay, so whatever we cover today will not show up on the midterm. But I would like to also mention that the midterm will include the content of homework number 3, and we will discuss homework number 3 tomorrow. Okay, so please take some time to start working on homework 3 if you haven't taken a look. But otherwise, any questions so far? Any question regarding the administration and the homework and the exam? If not, so let's slowly resume our lecture. Okay. Resume our lecture number 6. So lecture number 6, remember, is about difference equations, right? 差分方程式嘛, difference equation. And a difference equation is just by its nature, it is a linear system, and also if all the coefficients are fixed, 如果是固定的话, if all the coefficients are fixed, then it's a time invariant system, linear and time invariant. Okay? So we are going to use it a lot for the rest of this semester, at least for the coming month. Okay, we have quite a few examples how to design a difference equation so it has some desired frequency response. So that's kind of a major concern. So 我们主要关注的目标it's a major concern of this course, and we'll see that. So remember that a difference equation can be written as generally as that, with AK the coefficients, BK the coefficients, and output on the left and input on the right. On the right-hand side of the equation, okay? Difference equation with constant coefficients, and then what else? So, and then we know that we have a system function which can be written as bz divided by a of z, where b and a are both polynomials. 都是多项式, but polynomials. And so from there, we had we mentioned that without loss of generality, let's assume that the leading coefficient, 首项, the leading coefficient is 1. So we can just, if it's not, then we divide everything by a0 so to make it 1, right? So the reason why we suggest to assume that the leading coefficient is 1 is because then if we make this assumption, then we can keep only yn, the current term, the output we want to calculate. We keep it, and it only to the left-hand side of the equation, right? Just keep one term on the left-hand side of the equation and put everything else to the right. So then we have a formula. Then we have something that can be implemented by keep looking back to the past. You know, the current sample may depend on the past, as well as the current and past inputs. Okay, linear combination of input, linear combination of output that we produce, the system produces in the past. Okay, so this is the way we normally use the difference equation. This is a way we use a difference equation as a linear time invariant system. Right? Okay. So, and note that by writing the equation, by rewriting the equation, 重写, by rewriting the equation in this kind of expression, 用这样的表达式. In this expression, we essentially we are assuming causality, cause and effect, causal, 形容词, causal adjective, causality. The property of a system being causal, or causality, Causality means that every present sample depends only on values that we already calculated in the past. It doesn't depend on the future, because if it does, then this system cannot be implemented. Okay, yeah. In time, I mean, yeah. So by assuming causality, then we move on to write to just derive that the system function, which is written as bz divided by az, and where b and a are simply just putting the coefficients b0, b1, all the way to bn, putting the b coefficient in bz, and then we have a polynomial with the highest order being big N right here. And we have just similarly a polynomial a of z, which has a highest order of m by assumption. And then when hz is written as bz and az, it's rather easy to check that bz divided by az equals to the z transform of output divided by z transform of input. And therefore, this is called the system function. The system function, which is a rational function, if you will, rational. Something about ratio 除以一个东西叫 ratio, right? Ratio a b b ratio rational function. If you check the textbook, the textbook calls it a rational function, which means we have a ratio of two polynomials. A rational function, b of z divided by a of z, is our system function in that after z transform, the output equals to the input times our system function. Therefore, equivalently, in the time domain, what the output is input convolved with little h. And we know the relation between little h and big H. Big H is little h is the z transform of little h, and little h, this thing here, is our impulse response in time. Okay? So that's so much about having a difference equation and then construct the system function in terms of a ratio b of z divided by a of z, and where b and a are determined by the coefficients. Determined by the coefficient. So far so good. And we have an example of saying if I give you an h of z that looks like this, can you find the corresponding difference equation? Kind of in the opposite way, right? Given h of z, your task is to find the difference equation, and yes, we can do that. It's fairly easy. Just write down bz, az, and then voila. Do you know this person? It's French. Then here you go. Yeah, here you go. We have the difference equation right there. Okay? It's rather easy. And then the next last time when we met, we asked this other question. We asked that when we are given any arbitrary difference equation and write it in this way, okay, with yn being the only term to the left, everything else to the right. So can we calculate the impulse response like by hand? Okay. Of course, I mentioned that if we compute the impulse response by computer, certainly you can do that. Just keep the while loop running. You'll get one sample after another sample. Okay, so in computer, you can simply do it by simulation. But kind of by hand, can we calculate? Can we express the impulse response in terms of, let's say, a sum of several geometric sequences? 几何数列等比数列. And actually, actually we can. Actually, the solution, the form of the solution can be always written in as a sum of geometric sequences. Okay, so we'll be repeatedly saying this. The solution, the impulse response to any such kind of difference equation can be always written as a sum of geometric sequences. 几何数列的 let's say linear combination. Okay, so last time, to kind of show that this is true, we looked at one example. Okay, we look at one example where the current sample is equal to the sum of two past samples plus whatever input that we have currently. Okay, and we can easily see that just as an exercise, our system function b of z divided by a of z is equal to this. Yeah. And then from here, we want to make sure that the following steps are quite basic. I hope that everybody will learn it. Okay, everybody, please learn this. From bz divided by az, then the trick is that first we factorize the denominator, 分母的地方, factorize a of z into by this expression as product of something like z, 1 minus the root of a of z times z inverse. Okay, root 就是根啊 root 啊 1 minus the root of a of z, and you can always factorize any polynomial in this way, and that's called the fundamental what? Do you know the name? This is 代数的基本原理啊 the fundamental theorem of algebra 代数之基本原理 any complex coefficient polynomial has a root in the complex domain. It's very, very basic stuff. Yeah. Okay. And from there, if we can just find the root always exists. So the thing is that you find one root and then just factorize that out, and the polynomials, the order of the polynomial, 那个阶数the order of the polynomial becomes one lower, right? 就是不断的降就 keep doing this, we will lower and lower the order of a polynomial. In the end, we can factorize any nth order polynomial. In this case, we have second order polynomial. Now we all know that this can be generalized. For if the order is 2, then we have 2 roots, and if the order is 3, we have 3 roots, and so on. Okay. So, but in this simple example, because we have a simple polynomial, so we know a formula to find the roots, and just by applying the formula, you can easily find that d1, the roots d1 and d2 equals to 1 plus or minus square root of 5 divided by 2. So for those of you that are familiar, this ratio turns out to be the golden ratio, the 黄金比例, the golden ratio in Fibonacci series. This is the solution to this, actually the impulse response to this difference equation, of course, is the Fibonacci series. Right? Did you notice that? The impulse response, of course, is the Fibonacci series. Fibonacci series meaning that if the current input is, so we can expect you can expect the impulse response to be 1, 1, 2, 3, 5, and 8, 13, and so on, because the first sample, the current sample equals to the sum of the past 2 samples. Okay, so that's like if you do it by computer, sure you can do that. Yeah, and the solution we all know it diverges. The solution explodes to infinity. Yeah, but our trick, we are using this example as an example of how to solve a difference equation in general. Okay, so for this particular example, after we factorize, last time we talked about after we factorize a of z into that, then the next step is important. We will separate the product into a different way of this expression. Okay, this expression with 1 minus with one fact right here and the other factor right there, and now in the middle we have the summation. Okay, and then we have 2 unknowns to find out. 有2个未知数. We have 2 unknowns to find out, and in this homework, I I made it an exercise. Some of you might have learned this is in system signals and system. So there's a good way, a convenient way to find out, a fast way, let me say, an efficient, a fast method to find out alpha 1 and alpha 2, okay? Please, if you don't know what I'm talking about, please check the homework, okay? We will discuss that tomorrow, okay? But even without using the fast method, you can find it out, you know. You can find out alpha 1 and alpha 2 by what? By this. The kind of more straightforward, but not necessarily the fast way, okay? Not necessarily the fastest way is to realize that here we have the expression equals to 1 minus d1 z inverse, and you know what that's the other factor. And on top, what do we have? In Chinese, 就是通分嘛, yeah. In Chinese, we just put everything back to there and make these products. Alpha 1, we calculated the product of alpha 1 times the bottom right here, and alpha 2 times the bottom right here, and we summed it up, right? So on top, we have, this is what we have, alpha 1 times 1 minus d1, no, d2, z inverse, plus alpha 2 times 1 minus d1 z inverse, okay? And now we can force this term. We can force this term to be equal to 1. Yeah. When we force that to be equal to 1, and note that we already know the roots d1, d2. They are equal to 1 plus or minus square root of 5 divided by 2, right? So here, d1 and d2 are known. Alpha 1 and alpha 2 are unknowns. And then we have, when we force them to equal, then you can find out alpha 1 and alpha 2, because here 1 really is 1 plus, this is really is 1 plus 0 times z inverse, okay? So by comparing the coefficients, we can find out alpha 1 and alpha 2. Is that clear? 比较系数, comparing the coefficients. You can find out detail. And hopefully I didn't calculate, I had the right expression. Alpha 1, alpha 2, I can find it out. And there is a faster way of calculating the alpha 1 and alpha 2 in the homework, okay? So please check out the homework. But now when we take a look at this, now is h of z for our difference equation. For our difference equation, if h of z can now be written as, if h of z is now written as that, and now if you believe me that I've correctly calculated the alpha 1, alpha 2, all the coefficients, now everything's solved. Yeah. So I argue, here I claim to you, 我宣称, I claim to you that we can just use the formula in a reverse way, 倒过来用, in the opposite direction. This is the formula for geometric series, right? The sum of an infinite geometric series here is equal to that. Yeah. As long as the common ratio, as long as it converges with this criterion, okay? If we consider the sum over this region, this is a region on the z-plane. If we consider sum over this region on the z-plane, then the equality holds, okay? And at least for this part, okay? And similarly for this other part, the equality holds as long as we consider the sum in this region, okay, in this region. All right, so for the equality to really hold, okay, both criteria have to be satisfied. Is that clear? But anyways, this is to say that, sure, h of z being that can be written as that the equality hold as long as this region and that region has an intersection for certain regions. 它们有交集的话, if there is an intersection of the two regions, then we don't worry. Okay, just go ahead and write down the equality. And then, why do we want to write this down in this way? Because h of z, when we write it as sum of two power series, basically, 是幂级数, power series. Now we have the sum of two power series. Power series, or in Chinese, 幂级数. 幂 is the power. Power is something, the exponent. 了解吗? 次方数, power. 幂级数. When we write h of z as the sum of two power series, two power series of z inverse to be exact, we have z inverse here, z inverse square, z inverse q, and so on, okay? Two power series, and we know that by definition, by construction, h of z is z transform of the impulse response, right? This is by definition, h of z is defined this way, okay? And it turns out that a function, an analytic function, can have only one unique power series expansion. Okay? You cannot construct two power series that look different, but in fact they equal. No, it's impossible. Let me emphasize this kind of subtle point, okay, which I didn't really have a chance to talk about in detail. So there's a fact, a theorem in complex analysis, 在复变函数论里面, in complex analysis, there's a theorem that goes this way. When we consider an f of u that's which is a rational function, okay, in this, and we know that f of u, if we define f of u this way, where u, now you know that u in our context, u is the inverse, which is a complex number. Okay, so f of u is analytic at the origin. Analytic, meaning that this complex function is differentiable, okay, under the Cauchy-Riemann sense, Cauchy-Riemann 方程. Complex differentiable, analytic. Differentiable. Then the theorem tells us that f of u, this function, permits a unique Taylor series expansion around at that point where it is analytic. Permits a unique Taylor series expansion. Unique, that's the point that we can apply. Okay. You cannot just be so clever that to find another different way to write down the Taylor expansion, okay? Taylor expansion is unique, okay? You never have two different Taylor expansions which actually end up being the same, no. So the f of u, when it is analytic at a certain point, the function, then it permits a unique Taylor series expansion. So that means that we can write uniquely f of u as f0 plus, it turns out that it's this f prime 0 u plus 2 factorial at the bottom, f double prime 0 u square, and so on. This is Taylor series expansion, okay? So the way we apply, now the question, why does this matter? Is this something that we know and it doesn't help our life? 知道对人生也没有帮助 kind of. A lot of math is like that. It's not really helpful if you know it. But now we know it, we can have a peace in our mind. Yeah? when I write one way h of z as this, it's a power series expansion. And then we also know that by construction, h of z has this power series expansion by definition. And they are two things that look different, but they actually are the same, because the expansion should be unique. Okay, you don't need to work. Therefore, we can by just compare every coefficient separately. When two power series equal, that means all the coefficients need to be equal. That's the way we apply this theorem. Is that too fast? 就两个 power series when we have two power series, right? They look different. But if there's an equality, then every term has to be the same. Every coefficient, h0, the first coefficient, has to be equal to the first coefficient. The second coefficient has to be equal to the second coefficient, and so on. Okay? So therefore, we have a general expression. Finally, we have a general expression back in the time domain. That's the fun part. Okay? Now we have successfully calculated the impulse response. We have successfully found a general expression for Fibonacci series. The impulse response to our difference equation. And the general expression, if you write it down, is like that. And that we argue that this is a general expression for Fibonacci series. Is that correct? Okay, now it's your job to plug it in. Plus k equal to 0, plus k equal to 1 to see if this really is a general expression for the Fibonacci series. Okay. Any question? All right. So this is continuing from last time. Okay, we have the difference equation, one particular difference equation, and then this is the way we find out the corresponding impulse response if we treat the difference equation as a causal system. Okay? So there are a few more remarks that we can just observe from our solution. First is regarding stability. Stability, okay? Is this system stable? And the answer for this system is no. Because there are a few, now we want to mention a few equivalent statements. Okay? 有些等效的一些的 statement, okay? Stability, question mark, and the answer is no for this system. And because, you can write down because what? Because A, limit n approach infinity h of n is not finite, okay? It doesn't converge. B is because D1 and D2. Let me put like in general, okay? In general, we might have up to n roots, okay? And not all of them are inside the unit circle. Okay? Let me say that. Not all of the roots, which are we call the poles. In other words, the poles. Not all the poles are inside the unit circle. The unit circle, okay? And this is an important concept. Because each pole corresponds to a geometric series, a geometric sequence. While you are still writing, while you're still writing, I'm sorry, maybe, move it to the top, right? Not all poles are inside unit circle. So that means that once any of the pole is outside the unit circle, then we have a diverging impulse response. Okay? We have a diverging impulse response. Why? Because the pole location is a common ratio. Each pole corresponds to the common ratio of one of the geometric sequences. And in our case, we have two geometric sequences. Note that here, indeed, this is one pole and that's the other pole. right? This is one pole, and that's another pole. In this case, both of them are real, which is good, but one of them is greater than 1. One of them has the absolute value that's greater than 1. You can check that. 1 plus square root of pi divided by 2. That's larger than 1. The other one is smaller. Okay, so because one of them is greater than 1, the impulse response diverges. And therefore, the system is not stable. And I should also state that doesn't exist. I'm sorry, doesn't exist. I make a correction right here. Doesn't exist. Okay. The answer is no, because the limit does not exist. It actually, and equivalently, we find that the limit does not exist because one of the poles, at least one of the poles, is outside the unit circle, or equivalently we say not all are inside the unit circle. Okay? If one is outside unit circle, then the region of convergence, ROC, or the region of convergence, does not include the region of convergence of H of Z does not include Z, the unit circle. Okay, so these are 3 equivalent statements. Okay, they imply each other. System being unstable, some of the poles may be located not inside the unit circle, maybe on the unit circle, by the way. But here we don't have that to worry about that. Not all of them are inside the unit circle, and so the region of convergence does not include the unit circle. Okay, and so in this case, okay, actually the fourth way of seeing that the system is not stable, the final way, one other way of seeing this is to realize that the frequency response cannot be discussed. If the Z transform, if the region of convergence of our system function does not include the unit circle, then the frequency response of the system cannot be discussed. Okay? We have talked about that previously in our follow-up discussion, right? We have an example, unstable system, the frequency response cannot be discussed. Cannot be discussed. Okay, so that's a concept I want to emphasize. Okay, we often say that the frequency response basically is the DTFT of our impulse response. Okay, the DTFT of our impulse response equals to the system function evaluated on the unit circle. Okay, system function evaluated on the unit circle. Then we can write it down this way. Sure, if you evaluate it on the unit circle, sure, you get this answer. There's no secret. No, it's pretty straightforward. But we say it equals to the Fourier transform of our impulse response only if the Fourier transform of impulse response exists. Okay? If it doesn't, then please do not put the equal sign. Okay? So so let me complete writing. The Fourier transform of our impulse response equals to the system function evaluated on the unit circle if the system is stable. In other words, if all the poles are inside the unit circle. In other words, if D1, D2, D blah, 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 Dn, if all the poles have an absolute value that are no more than 1, okay? The radius of the pole, where they are located on the z-plane, if all the radius or the radii, all the radii are smaller than 1, then we see that system is stable. For transform of the impulse response exists, then we can talk about frequency response. Okay, this is important. For a system like for Fibonacci, which produces Fibonacci series, please do not talk about its frequency response. Okay, please, yeah. Can we agree on that? Unless you want to let the time go backward, we will talk about that later, okay? When the time goes forward, the Fibonacci series explodes. It doesn't make sense to talk about frequency response. The gain is always infinity. For any little input, the system diverges. Gain is always infinity. It doesn't make any sense to talk about frequency response if the system is not stable to begin with. Okay, yeah. All right, so far so good? Yeah. Okay, so there's also the question is, now we just keep telling you that it's important to look at the location of the poles, right? This is kind of the main message for the past 20 minutes I'm trying to deliver. Please be aware of the locations of the poles. We want them to be all inside the unit circle when you design a system, for example. But what if our system simply does not have any pole? What if our system just simply does not have any pole? Any suggestion? What kind of system is that? What if our system simply does not have any pole? Then good news is that the system is always stable. Okay? The system, if it doesn't have any pole, then the system is always stable. Equivalently, h of z, h of z, now if it doesn't have any pole, that means a of z is equal to 1. So h of z is simply b of z, okay? Is b0 plus b1 z inverse plus maybe up to several terms. It's a polynomial, okay? When the system is like that, that means the impulse response. What is the impulse response? Can you draw a sketch of the impulse response? The impulse response has what? Only so many non-zero terms. Okay? Only because the first hand, again, by that little theorem that we just introduced, then that means H0 is B0, H1 is B1, and so on. We have up to n plus 1 non-zero samples when the system receives the delta function as its input, right? The impulse response has only so many non-zero terms. Its length is finite. 长度是有限的啊. The length is finite, so we say this is an FIR system. I will come back to this. Finite impulse response. Yeah, I shouldn't put a hyphen right here. Yeah. Finite impulse response system. Or we say this is an FIR system. And an FIR system has no pole, so it is always stable. Okay? It is always stable. Okay? Yeah. So that's a kind of first discussion item. Okay? FIR system is always stable. The system has no pole. It's always stable. Are we good? Yeah. So now another property I want to mention is that you know that when we are given a polynomial, like a of z, when a of z is a high-order polynomial, okay, just chances are some of the poles should be complex. right? You'd be pretty lucky if you just randomly write out a polynomial and all the roots are real. That's more rare. That's not so often. It doesn't happen so often, right? So you can imagine that when we randomly design a system with B of A of Z, we want to locate all the poles, and some of the poles got to be complex valued. 会有复数. They may have imaginary parts. That makes sense, right? When we design a system and write down A of Z and find out, oh, some of the roots got to be, some of the poles got to be complex. Yeah, you might find out some of the poles should be complex. Okay. And a kind of a small note right here. Even if all the coefficients AK that we begin with are real, right? Yeah, real valued, real coefficient polynomial may have complex roots. Of course, yeah. But if all the coefficients are real, if all these coefficients in the difference equation, if they are originally real, then the roots, complex roots may well occur in conjugate pairs. 会都是共轭复数. If you have one complex root and then its complex conjugate got to be also a root. Okay? So they occur in conjugate pairs if any root is complex. Okay? That will happen if all our coefficients are real to begin with. That clear? Yeah. Then DK are either real or they occur in complex conjugate pairs. 共轭复数. Let me write down the Chinese 共轭复数. 共轭. Complex conjugate 共轭复数. So now, when they do occur in conjugate pairs, let's say that we have dk and dk bar. So we have dk and dk bar, where the bar in here means the complex conjugate. Okay? dk and its complex conjugate are both poles of our system. Then it turns out that the impulse response may well contain a term that looks like this. Okay? R to the nth power times cosine of a frequency times time index n plus there may be a phase shift. And this is part of our homework number 3. Okay? Check it out. This is homework number 3. Part of it is I asked you to figure it out, okay? To figure out that how when the impulse response contains a term like that, yeah, we can construct a difference equation whose impulse response looks like that. Okay, you can do that. Okay, and you see that this happens when we have two complex conjugate poles. Okay, you'll show that. Okay? So that's part of our next homework. And please, if you're interested, please work it out. Okay. Yeah. And it makes sense because cosine by Euler's formula, cosine equals to what? Cosine equals to something plus another thing divided by 2, right? And those two things are geometric sequences in this context. Okay? So it's still true that we say the impulse response of a difference equation can always be written as sums of geometric series. Still, yes, as linear combination of several geometric sequences. That is still true. But just turns out that some of them, when they add up, they equal to cosine. Okay? Don't be surprised. Okay? Some of the impulse response may contain terms like this. That's all I want to say. Okay? So far, so good? Yeah? Okay. And the final comment I have right here, okay, the final comment regarding difference equation is to realize that here, let's say, in any linear and constant coefficient, CC, constant coefficient, okay, in any linear constant coefficient, 常系数了, constant linear constant coefficient, difference equation. Okay? It turns out that time can also go backward. And even though I don't recommend thinking this way, but if you insist, 如果你坚持的话啊 if you insist, when we write down any difference equation, you can insist, if you will. I cannot stop you. This is a country with freedom, okay? 自由的国家啊 you can insist. Time can also go backward because the difference equation itself, by itself, it does not specify how, whether time is going to go forward or backward. It's depending how you use it, okay? So I want to just summarize by mentioning that time can also go backward in any given difference equation. Even though I won't bother to discuss this interpretation. What interpretation? Let's see this example, okay? Here's a very simple example, an LCCDE. Difference equation with feedback term, yn equals to 0.8 times the previous sample plus xn. This is a difference equation, right? But did you realize that we can rewrite the equation into this form? Yeah, take a look. Yeah, this is one equation. This is the same equation. They are the same equation, okay? Yeah. But when we write it down this way, we sort of imply, now we are implying that the past sample depends on the present sample. This is sort of a kind of a 催眠, kind of an implication. When we write it this way, are we implying that the previous sample, yn minus 1, should depend on the present sample? And of course, there's a change of sign in here, if you're careful. Okay? But otherwise, they are the same equation, right? Same equation, what's going wrong? What's wrong here? Nothing's wrong, okay? Mathematically, they are really the same equation, okay? But sort of what's different here is the way we see it, okay? The way we see it, because we are all programmers, right? Any of them is not programmer, you'll say 不是 programmer. Everybody is a programmer, right? Or wrong? Or you guys are being too humble, yeah. You're not sure if you're a programmer. But we're all trained to see an equation as this way, like whatever you put in on the left-hand side of your code, right, should depend on something to the right of the equation is something you need to take action, something you need to calculate. Okay? So when we write down this way, we are all we are trained to see an equation as if this is a line in your code. Okay? That's fine, yeah. So seeing the equation this way, but now we move this other thing to the left-hand side. Yeah, this is sort of implying that we are calculating yn minus 1 using the expression to your right. Okay? And this is problematic, okay? This will be problematic because this program cannot run in real time, okay? The program can be, you can calculate it after recording your signal, okay? But not in real time. So in DSP, this cannot be implemented. This is a kind of non-causal interpretation of the same equation. So causal, non-causal is just a matter of interpretation, okay? And in this semester, I emphasize on causal. So we always assume that we are going to use a difference equation in the causal way, okay? Please avoid using this, okay? But when you do it, then a lot of funny things can happen, okay? First of all, the impulse response. What is the impulse? For example, I'm not going to talk too much about this. For example, if you insist, sure, then the impulse response becomes what? Becomes non-causal. That means the first term at time 0, then time minus 1, we have something. I believe it should be 1.25, and then time minus 2, higher, time minus 3 even higher. It grows as time goes backward, okay? It grows as time goes backward. And I hesitate, okay? I don't want to emphasize on this interpretation. But here, just for the sake of being complete, to complete the lecture, I want to mention that causal, non-causal is a matter of interpretation. 是一种诠释啊 is a matter of interpretation. In this class, we recommend the causal interpretation when we use a difference equation. When we design our system in terms of a difference equation, we use it. We will use our system, use the equation in the causal way. Okay? All right. So that concludes this lecture. So, and the next hour, we'll move on to a new lecture. Okay? Yeah. Let's take a break of 10 minutes. Okay, so the TA and I are just discussing how we manage the midterm exam. Okay, so we have it will be you need to come to the classroom. Okay, either this room or the next room, and I just suggested to TA that they will announce who goes to this room and who goes to the other room. Okay, so they will make an announcement, probably based on your student ID number. Okay, so that's one thing, and I haven't finished designing the exam. Okay, 我还没有那个出好题目。Okay, yeah. But yes, please review your homework and mainly the homework and the follow-up questions. Okay, yeah, mainly, yeah. Okay, so let me make a correction, a small correction of an error right here. So here we need to add parentheses right here. Okay, so I made a mistake. Please correct it accordingly. But otherwise, let's slowly get into this next lecture. Okay, I probably won't be able to complete this lecture, but this lecture will be the beginning, the first example where we are going to design a system. Okay, we need to introduce a tiny little bit of design thinking. Okay, so this is the first example of design. It's not going to be a good design, but nonetheless, it's a design. We can say that we are going to design a system, right? Finally. And so that's this lecture. And so before I move on, I want to also mention that so next Wednesday, we have the first midterm. Next Thursday, let's just simply have a lecture, okay? So next Thursday, please come back and we have a lecture, okay? To just probably continue working on this lecture number 7, okay? So that's the plan for next week. So now lecture 7, the title here I have is filter design, okay? This is a way of designing a filter, and particularly we are going to design by looking at an analog impulse response. But no, 这写错了，这文法错了啊 you know by sampling analog the impulse response. No, that's wrong, definitely wrong. Okay, you know that is wrong. Right? By sampling the analog impulse response of a certain system that we like. Say that you're in love with the analog system and you want to simulate that analog system in the digital domain. You can do that and by sampling the analog impulse response. Okay? So here, let's begin by looking at this sort of workflow. This is a workflow, and on the left, at the left, you see that we receive a continuous time signal, right? Again, this is a notation. XC, C stands for continuous, right? And we're going to convert it to the digital domain, right? C to D, or discrete time domain, yeah, or A to D. With the sampling period, okay? How often, this refers to how often we look at we make the measurement, okay? How often we perform sample and hold, right? Sampling period T, and then we get a discrete time signal, which we denote as x of n. And then the idea right here is that we are going to process our input using an LTI system, using a linear and time invariant system to process our signal and then produce an output. And this system is going to produce an output, and the output might be denoted as y of n, produced by the system. And then you can just apply D to C conversion to make it go back to the analog domain, which we denote the output signal in the analog domain as y continuous time of t, yc of t, where c again stands for continuous. So that's a kind of a general framework of digital signal processing, of digital filtering, basically, okay? We are going to design an LTI system. And in this example, and in most other examples we will encounter in this semester, most often we design the LTI system by finding a difference equation. Almost always. 100%, I should say. 100% when we design an LTI system in my life, okay, I'm going to find a difference equation, okay, seriously, right? At least for this example. So now let's specify our design goal, okay? Suppose that we have an example of a continuous time system. If we have an analog system whose impulse response can be written as such, suppose that we have an analog system whose impulse response is A times an exponentially decaying signal, okay? A being a constant. Suppose that we have a system whose impulse response is A times exponential decay as a function of t, okay? For t after 0. And before 0, the system is causal, the impulse response is 0. It's all 0 before time 0, okay? But after time 0, we have the impulse response jumps to A, and then it starts decaying with a factor of alpha, with a rate, decaying rate of alpha, okay? So let's use this as an example. Suppose that we are in love with this analog response, and we like it so much, we want to simulate this analog system in the digital domain. Yeah. So analog being reality, digital being digital being the virtual, okay? So we can simulate this response in your computer, or better, in your computer game, if you will, okay? Simulation, right? Yeah. Put on your goggle and experience this analog impulse response, right? Okay, so to put things into sort of a context, okay? What kind of response is this? What kind of reality is this? What kind of reality do we have right here? So I'm going to give you one example, okay? So we might be simulating a circuit, right? An analog circuit. This very simple circuit with one capacitor and one resistor, okay? So imagine that if we put in an input, if our input is a current that we can control, if we just deliver this current to this circuit with resistor and capacitor in parallel, okay? What's the output voltage, right, across this impedance? We have a parallel connection of resistor and capacitor. And we are just feeding a current which we can control, using that as an input and to produce a voltage drop across our impedance, right? Then what's the output voltage? You know, this can be something you want to simulate, right? In discrete time, okay? Can we simulate this this analog system in discrete time? That's the question, okay? Now to develop this further, okay? I claim to you that for those of you that are familiar with circuits, delusion, you know that this is a charging process. You're charging a capacitor with a current, right? So just kind of the standard way of handling this is in the Laplace S domain, okay? So for those of you that are familiar, we can say that now we have one capacitor whose admittance, 导纳, okay, admittance, in the Laplace domain should be written as S times C, right? That's the admittance. That's the admittance of a capacitor, right? Equal to SC. Yeah. And the admittance of a resistor is simply the conductance of that resistor, right? 1 over R, that's the conductance. 导纳啊 conductance 电导啊 the conductance of a resistor is 1 over R. So when we put them, the capacitor and the resistor, put two things in parallel, their admittance adds, right? The admittance added in parallel when we have two things in parallel, right? In parallel, so then we know V equals to I times impedance, okay? Then the impedance is simply 1 over, the impedance is simply 1 over the admittance, okay? So when we multiply our current in the Laplace domain with the impedance, now it is 1 over that, then the resulting voltage drop in the Laplace domain is the Laplace transform of the voltage. Okay, it should be fairly straightforward if you know Laplace transform. Okay, but then if we allow me to kind of reorganize our terms a little bit, so I still right here, but here, let's extract 1 over C right here to the outside. And then the inside becomes S plus a factor, a constant alpha, where alpha is 1 divided by RC. This should be pretty straightforward, okay? Here we have I of S times a constant factor, 1 divided by capacitance times this factor right here, which is important in Laplace transform, okay? So this is how the system function looks like in the Laplace domain. So we apply inverse Laplace transform. Now, if we apply inverse Laplace transform of H of S, okay, then we see that in the continuous time, the voltage should be, the output is a voltage, should be equal to the input, which is the current, convolved with the impulse response. Right? And what is the impulse response? The impulse response is the inverse Laplace transform of the system function. Okay? And for those of you that are familiar with Laplace transform, you know that when you see this expression, at least when I was in college, I learned to memorize. Okay, I literally memorized that the inverse Laplace transform of 1 over S plus alpha is equal to the unit step function times exponential minus alpha t. This is something that I memorized when I was like your age. Okay, please do the same. Do the right things, do things right. Okay. Any questions so far? So the input voltage is current convolved with this impulse response. Okay, and this impulse response is what the system produces when it receives the delta function as its input. And does that make sense? It makes a lot of sense. Okay, I argue that this makes a lot of sense. Why? Because I'm arguing that this makes a lot of sense because, when we receive a delta impulse, when this is a circuit, okay, which we are in love with for this next hour, okay? This is a circuit and we deliver a delta function. That means instantly this impulse is going to charge that capacitor. The capacitor will be charged instantly with the charge, amount of charge accumulated over this capacitor is going to be 1. 1 unit of charge is going to accumulate over that capacitor. Okay, so if 1 unit of charge, 1 coulomb, if you will, 1 coulomb of charge is going to accumulate instantly over this capacitor. So now we know that when we have charge over that capacitor, then the voltage instantly on that capacitor is simply the charge divided by C, right? Q equals to CV, right? Q being the charge, C being the capacitance, and V being the voltage, right? So voltage across that capacitor. Right, so now if Q equals to 1, we have 1 unit, 1 coulomb of charge accumulated over this capacitor, then instantly we have what? We have 1 over C of voltage dropping over that capacitor. So that's why, yeah, indeed, initially we have 1 over C. Therefore, initially, h of t initially should be 1 over c at time 0. And then it decays exponentially because of current leakage with a time constant of RC. Yeah, for those of you from DNGC, by this time you should know that, that's bad. But of course, it's not a linear drop. I don't like it. Need to draw it faster. Okay, of course, there is going to be an exponential decay with a time constant tau equals to RC. And time constant is simply 1 divided by alpha, the decay rate. Okay, alpha has a unit of 1 over time. Okay, decay rate equals to 1 divided by RC, which is right here. The decay rate. The decay rate in that impulse response is going to be 1 over RC, and that's the way it is. Okay, it makes a lot of sense. Yeah. Okay, so now move on. Now, since we agree that we are quite interested in this circuit and we want to simulate it in the digital world, in your computer, with a processor. Okay. So now the idea is now let's sample. Idea is now we design the impulse response in discrete time. Okay. I'm going to suggest. Here's my suggestion. I suggest that we sample our continuous time impulse response. We sample h of t at integer multiple of the sampling period. Okay? Essentially, that's what I suggest we do. I suggest that we sample h. Yeah. But then there's also a kind of a factor here that's not all that important, but I recommend leaving it here. Okay? We will sample our impulse response, which look like that, and then we call the result h of n. And note, my first note, okay? My first note that this is, I argue this is a design. This is a design. I argue that this is already a design. It's design thinking. We have a desired, 想要的, desired. We have a desired system in analog. I want to mimic its behavior by sampling its impulse response, and the result becomes a sequence. Okay, and I argue that this is already a design. Okay, yeah, this is already a design in what sense? In the sense that we are going to use this impulse response in the discrete time in this way. Then we are going to, for any discrete input, we are going to convolve that input with this new, with our impulse response in discrete time, and argue that this is already a design. Okay, this is already a design. This is already designed because the resulting system is something that you can implement and study its frequency response and so on. Okay, yeah, already a design. In that this is the way we are going to use it. The resulting system, h and you'll see that the resulting system, okay, after the transform, you can construct a system. You can construct a system whose impulse response is ready for you, ready right there to convolve with our input. Okay, this is a system. This thinking results in a system that you can use. Okay, so that's why, in that sense, it will be clearer that we will create a system which we will use. Okay, but now the question is the resulting system when it produces an output. When it produces an output, does the output resemble the actual output, the desired output that we want to simulate? Okay? does the output resemble the output sampled at integer multiples of t? You know, the desired output here, we have the input, and we are going to sample our impulse response using this design thinking. But then we need to ask a question. Then the resulting output in discrete time, y1, y2, y3, y4 in discrete time, will that resemble, will that approximate, should I say, will that approximate the actual output, the desired output, also sampled at integer multiples of our sampling period? That's a question. Yeah. You can design a system, but you need to question your design. You know, I claim that this, I claim to you, 宣称嘛, yeah, I claim to you this is a design. You need to question me. Does your design result in a good approximation of the analog system? The analog system is a circuit, but by moving everything to the discrete time domain, will my system now, my digital system, produce a result that's similar to this analog system? Will it be a good approximation? That's a question you can ask me. Okay. My design might not be perfect. Okay? It's never perfect. Okay. Yeah. So we'll repeatedly seeing this. Now, we'll repeatedly ask our question when we approximate an ideal low-pass filter. Later, you'll learn that. Okay, how good is the approximation? The approximation is never perfect. Okay, and yeah, but here we have an insight. Okay, we have an insight that maybe the chances are, yeah, we might be getting a surprisingly good approximation. Okay. And I have kind of a reason for that. When we sample, so now our system, my recommendation is to sample our analog response. Okay, sample our analog impulse response and call it h of n. Okay, when we do that, and then note that here I'm going to argue that indeed yn approximates y continuous n sample at nt. Okay, so in the next few lines, I'm going to use Riemann sum, use this concept to convince you, to sort of argue that yeah, the approximation really is a good one. Okay, there really is such an approximation in the sense of Riemann sum. So how did that go? Note that y of c sampled at nt, okay? The analog output sampled, the desired output sampled at nt, that should be equal to the input convolve with the h of t, convolution but sampled at nt, right? That's by definition. There's no secret in here. That's just by definition, okay? But then, when we write down what is convolution, there's also no secret either, okay? No secret here. Convolution means, and we, x, h, and we let the time go backward for x, for one of them, h of t, yeah. So here, and evaluated at time nt, right? Convolution evaluated at time nt means that tau now being the dominant variable, but the convolution eventually is evaluated right there at nt. Is that clear? Yeah. There's also no secret right here. Okay, so far so good. Yeah. But now the next thing is Riemann approximation. Here we have an integral, 有个积分式啊. You all learned in calculus that what does it mean to make an integration? What does it mean to calculate an integral? That means we all learned that the area what? Integral is an area under a curve, right? Integral is the area under a curve, okay? So let's draw a picture. Suppose that we have this integral. Now we have this integral, and we want to kind of draw a picture of what does it mean to calculate the integral? That means that we are calculating an area under the curve, okay? Calculate the area under the curve, and we know that area under the curve can be approximated by 长条图嘛, You know what I mean? Area under the curve can be approximated by sum of the area of all the stripes right here. 长条图. All the stripes, all these rectangles, the sum of their area should be to approximate the area under that curve. And the approximation error under good conditions will approach zero. The error will approach zero when we have what? When we cut the time finer and finer, right? When this delta t, when this delta t is small, then the approximation should be good. That's all we have learned. You must have learned it in your calculus, right? 在微积分一定有学过啊。Integral meaning to calculate the area under the curve, and how do we calculate that? One way is to, we all learned this, that the area under the curve can be approximated by sum of rectangles. And then when we take the limit of delta t, when delta t right here, when delta t approaches is small enough, when delta t is sufficiently small, then this approximation should be good. Okay, so let's write down this approximation. We are going to approximate the integral by sum area. What sum? So here we evaluate this. We evaluate this at integer multiple with we replace integral with the summation index m. Okay, replace it, and then here this t really is delta t right here. Okay, so idea is that now we have 0, t, and 2t, and so on, and this is m times t. 0 minus t minus 2t, and so on. Okay, so that's why I mean that we are evaluating this expression, but at time equals to mt. This is tau equals to mt. Make this substitution, then we replace the integral with the summation. Okay? We are replacing the integral with the summation, and then this is the kind of the function value, the value of the function, the integrand, whatever inside this function we want to integrate, replace it, evaluate it at integer multiple of our delta t, and then that's the height of a rectangle. Each term is the height, 这个高度, the height of the rectangle, and what's the width of the rectangle. The width, 宽度, the width of the rectangle is simply t. Here big T is delta t, okay? So this is a Riemann sum approximation. Let me write it down. This approximation is the Riemann sum. Approximation. And we know that at least roughly speaking, 大致上来讲, roughly speaking, the approximation is good if t is sufficiently small. Right? The approximation should be good, and it should be good. A good approximation if t is small. Okay? If t is small. But how small is small? Any suggestion? Yeah. We know that t is good if it is sufficiently small. But I need your opinion. Can anybody tell me? 保证没加分. Today is not Thursday. Okay. How small is small enough? We know that t needs to be small, but how small is good enough? How small is small enough? Any suggestion in this context? T needs to be at least 10 times smaller than what? Than. Any suggestion? How small is small enough? if we want to simulate this circuit? Any insight? Anyway, it needs to be small enough, okay? Make it 1/100,000,000 1 microsecond, I don't know, yeah. Okay, t needs to be small enough. You want to simulate the behavior of an analog circuit, okay? Small enough. Now, let me just complete my writing. If t is small enough, okay? Small enough. Maybe we can have a computer exercise, but yeah, don't worry about it for now. But anyway, so in principle that we know. Now, let me complete this derivation. Now, take a look at the result we have right here, okay? Let's come back to this expression right here. This is nothing but the convolution. This actually equals to x n convolved with something. With what? T times. Yeah, this is really, it equals to, this is equivalent in the discrete time. Now we are convolving x with something. Did you notice? We are convolving x with what? With h. Why? Because we have defined, I have suggested to you that x h of n is defined as t times the continuous one evaluated at integer multiple of t. Because this is the way we define h of n. Do you notice? Okay, so let's organize our thoughts a little bit. 我们来整合一下到底 what's going on right here. Okay, let's organize our thought. So, at first, I suggest that this is a design thinking. Just by intuition, I'm suggesting that let's sample the analog. Maybe I need to, be careful. So let me just improve my notation. Okay, here maybe I should put C right here. Okay, let's say h continuous of t is like that. Is our desired impulse response, and we are going to sample it so that becomes the sequence. Okay, let's sample our analog response, and the resulting discrete response is denoted as h of n. So I'm going to make a suggestion. I recommend doing this. Okay, the textbook recommends doing this. Okay, this is one example from the textbook, and this is design. And then based on that, when I'm arguing that now now the thought actually goes backward. Let's try to go backward in this direction, okay? So now with this design thinking, y of n should be equal to ax convolved with our h, right? And x convolved with h equal to this. And that's a good approximation to this integral. And what is that integral? This integral is x of t in continuous time convolved with our desired analog impulse response. So this is the way we can kind of convince ourselves. This is an evidence or a support. Okay? This encourages us to think that, hey, our design is a good one. Because by definition, it's a Riemann sum approximation of that integral. Okay? Because of that, our system, our discrete output should be approximately equal to the desired continuous output sampled at NT. The thought actually goes backward. Design thinking. Okay? It's never going to be perfect. I mean, the design is good only if T is small enough. Okay? Only if T is small enough. We have learned that T needs to be small enough. The sampling rate needs to be high enough, right? We have learned that. So at least you can partially answer my question. The sampling rate needs to be higher than what? Higher than 2 times the highest frequency in your input. Okay? So please do not deliver your input to to fluctuate too rapidly. Okay. So going back to the previous chapter 4, okay, we know that at least t, how small is small enough? T needs to be fast so that it covers 2 times the Nyquist frequency of your input signal. Okay, that's one thing. And another criterion, I should say that we will keep coming back to this. Okay, T needs to be fast enough to simulate this decay. Okay, so if this system decays with RC equal to, let's say, 10 microseconds, then your T needs to be shorter than that. Does that make sense? If your analog system, your desired system to simulate, if that impulse response decays with an RC time constant of 10 microseconds, then your T right here, the big T right here, your sampling period has to be smaller than that, or way smaller than that. Okay, we're talking about like at least 10 times smaller than that, maybe even smaller. Okay, yeah. So the kind of design thinking when we need to put things together, a lot of different factors need to be considered. Okay, we need to consider how fast your input, what kind of input we want to handle, and what kind of decay we want to simulate. The T needs to be small, okay, or bearing on the small side, okay. When we design, if you can afford a small T, go for it, okay. That means a faster clock rate. If you can afford a fast clock rate, please go for that, yeah. To avoid problems, or avoid complications, okay. Yeah, any questions so far? And so now we have about 10 minutes. Okay, let me just give you some highlight. Okay, we'll continue this discussion next week. Okay, I want to give you a highlight. Now I've convinced you. Hopefully, I've been trying to convince you that this is a nice design. Okay, this is a nice design. It turns out that you can turn this h of n into an h of z. Okay, you can turn that into an h of z, which should look like again 1. Actually, TA divided by 1, and yeah, because I'm so used to it, minus alpha t z inverse. Yeah. Turns out that you can check the equivalent system function is that, and then we can turn this into, we're ready to turn this into a difference equation. Okay? The difference equation should go this way. Y of n should be equal to some kind of factor times the previous sample y n minus 1 plus ta times x of n. Okay, a of z, b of z. Turn that into a difference equation, and then you can check that here is good. That note that this pole is smaller than 1. Of course, if RC, because we are having RC decay. Yeah. Of course, this is a stable system. We have a kind of our design is guaranteed stable. That's a good property. So next time we'll see that, and then we can discuss the frequency response. Okay, because the system is stable, our design is essentially is intrinsically stable. It's always stable. Then we can talk about the frequency response. Okay. We can talk about the frequency response, and we'll draw that. It turned out that the frequency response, next time, we will talk about the magnitude response as well as phase response next time when we meet. Okay? So that's kind of preview. Indeed, we are trying to simulate an analog circuit. Okay? And we call this way of design, it has a name. This is a design by sampling the analog impulse response. Okay? Designing a discrete time system. Okay, so that's what I want to continue working on next week when we meet. But anyway, tomorrow, please prepare for homework number 3, and I've asked the TA to announce the signed-up sheet, right? The sign-up sheet. So let's meet. I'll see you tomorrow. Okay, see you tomorrow. Yeah, see you. Thank you. Yeah. 没有，对啊。
我写作业的时候发现他 yield.